All right, welcome to part 2 of sedimentary rocks. We're going to transition in this section to thinking about chemical sedimentary rocks, Steno's principles, and some paleo-environment reconstructions. You've had this question in your mind of how the world around you would look as a rock if it were suddenly buried and lithified. So now we can consider, is that world, could it be a chemical rock, either biologic, or an evaporite or a carbonate? And then we'll think more about kind of the ordering of that future rock with other rocks. Okay, so now we move on to chemical sedimentary rocks. Just like the clastic rocks, these do require some weathering and erosion to produce the ions. However, we're going to be thinking of these more in the chemical weathering realm. So if you remember from the hill slopes lecture, chemical weathering was the kind of chemical breakup of the original rocks, and they could form an ionic load. So this could be the complete dissolution of rocks, or they could form secondary minerals, which we mentioned were mostly clays. And so that's how we get a lot of the material for the shales that we talked about in clastic sedimentary rocks. But the major difference between clastic and chemical is that we're not going to necessarily have deposition and lithification in the same process. Rather, we're going to have evaporation of brines, precipitation of minerals, and we're also going to have some organics involved in this. So maybe deposition of organic material. So we'll go through each of those 3 different processes, starting out with evaporites. This is a subgroup of chemical sedimentary rocks. They essentially form as we have an ion-rich water, which we could also call a brine, which starts to evaporate. And as it evaporates, the ions are left behind. The remaining water starts to saturate in those ions, and evaporate deposits precipitate out of that brine. Because this really needs a situation where you can saturate the ions, this tends to form in closed lakes or protected inlets where there's not a refreshment of the water flow. So some examples of places where we see evaporites forming are playas and other lakes that are completely closed off. And then we can also see this in protected inlets. So this is kind of a side view example of what one of these inlets might look like, where there's some barrier that stops too much flow between the two. So you may get some new liquid coming in, but it's not enough to sort of mix the basin. And so the basin ends up experiencing evaporation and saturation in the ions. Most evaporites are going to be originating from seawater. And that seawater is going to contain a lot of salts in it, mostly sodium chloride, but some magnesium chloride and calcium sulfates and calcium carbonates. And so based on this original seawater concentrations, we're going to get key evaporite deposits. And these evaporites form at different times based on their own unique solubility. So it's not necessarily related one-to-one with the original concentrations of the seawater. So if we start out with a basin of seawater and start to evaporate it, after about 50% of that water is evaporated off, we'll start to see some carbonates forming. If we evaporate off another 30% of the original water, we'll get a mineral called gypsum, and then another 10% will get a mineral called halite. The rocks that are made of the minerals gypsum and halite are called gypsum and halite. So this is an instance where we have a rock composed of one mineral. The order in which these evaporate is going to form a unique pattern in that basin. So if we look at a closed basin, so this would be the example of a playa, as the playa evaporates, the first evaporites are forming on the edges, and that's because the body of water is shrinking. So by the time the calcium carbonate is forming, the body of water has shrunk to encapsulate kind of the outline of the gypsum. As more evaporation occurs, the body of water is shrinking even more, and that gypsum is left behind where it has shrunk. And so we get the water level at time 2, we'll call it. And then further evaporation of that water is going to lead to crystallization of halite. So in contrast to this, if you have some connection with an ocean or waterway, your water levels aren't necessarily going to drop. So instead, what you'll see is that the calcium carbonate is forming first, and so that's forming on the bottom. And then the next formation is gypsum, and then halite rings it around the edge. So some interesting stories that we can tell with evaporites include I think it's fascinating, the Mycenaean salinity crisis. So around the Mediterranean, there are a whole series of halites and carbonates that are found. And these evaporite deposits indicate that sometime during the Mycenaean time period, which is about 5.96 to 5.33 million years ago, the lake or the Mediterranean Sea must have become cut off because it was suddenly evaporating in this, like this second scenario here, where there is no clear communication and mixing of ocean water with the Mediterranean seawater. So this gives us some clues that this became a closed basin. From the pattern, so we have halites in the center and carbonates ringing it. That can give us some clue about how this formed. So if we look back, if we have carbonate on the outside and halite on the inside, that is this bullseye pattern of part 1. So this indicates that rather than having a small inlet that connects the ocean to the Mediterranean Sea, during the Mycenaean crisis, we actually had a complete blockage there. And so the Mediterranean actually became isolated from the rest of the ocean and saltwater system. Also, a neat aspect of this is we can see evidence of how that connection was breached, or how that connection started up again. So at about 5.33 million years ago, the end of the Mycenaean, sea level rose, and as it rose, it breached the barrier into the Mediterranean and ended the salinity crisis by replenishing it with more water. But this event turns out was really dramatic. It's called the Zanclean flood, and it is an example of a mega flood where, rather than our normal floods with, some large amount of water coming through, we get floods with 10 to the 6 cubic meters per second of water coming through. So just kind of out of this world, extraordinary events. And what's really neat is we can see evidence of this throughout the Mediterranean in the form of erosional channels. So there's, in this image, in the center top here, we're looking at a canyon. So here's the outline of the canyon. And the water was rushing over the top of this canyon and likely cut it right from kind of the edge to its current position, cut all of that during the Zanclean flood. You can see this in a side view in B, just below that. We also see signs of this erosion in the subsurface record. So this is an example where we've taken a seismic imaging of the sediments in the Mediterranean Sea. Each of these lines represents some bedding of the sediment. So you can see this is kind of a normal bedding structure where everything is continuous across. And we see this purple line here where the bedding is suddenly truncated and cut away. And that's interpreted as where the Zanclean flood cut through and slice through all of this sediment. So I think that's a pretty cool story that we can reconstruct from our initial clues to this. We're just looking at the order of evaporate deposits, and that led people to then look for evidence of this flood that replenished the Mediterranean Ocean, ended the Messinian salinity crisis. We also get things like salt diapirs forming from evaporite deposits. So if we have evaporites that are buried by clastic sedimentary rocks, we get a buoyancy difference. The evaporites tend to have a lighter density than the clastics on top of them. And so they will tend to try and rise towards the surface, kind of like you see here where the salts, the halites, are rising up in what's called a salt diapir. We can also call this a salt dome. These are fairly important economically because these often trap natural gases like oils at the top. And so when we see things like salt domes, like these salt domes in the Gulf of Mexico here, that's often an indication that there's some natural gas reservoirs nearby. And so these locations are often pinpointed for natural gas drilling. So these are the domes you can see. I just got this image off of Google Earth or Google Maps. So if you look offshore in the Gulf of Mexico, you'll see these really cool dome shapes. And that's from these salt domes that are rising up towards the surface. When they do breach the surface, they look like salt. So here is an exposed salt dome in Iran, and you can see it's white, just like your table salt is, especially contrasted with the surrounding rock. Right, another main type of chemical sedimentary rocks are carbonates. So these are going to include a lot of, carbonate, and that carbonate is usually bound to either calcium or magnesium. So a calcium carbonate is a calcite, and a magnesium carbonate is a dolomite. Calcite as a rock is called limestone, and dolomite as a rock is a dolostone. So these carbonates can be created through evaporation. So we just talked about carbonates as being the first part of that evaporite cycle in the last few slides. They can also form through precipitation of dissolved CO2 or through biologic activity. So a lot of shells are made of calcium carbonate, and so as these kind of deposit together and then lithify, they form a carbonate rock. All right, so since we already went over evaporation, we'll talk about precipitation and the biological precipitation in the next few slides. So in the ocean water, we have CO2, we have water, we have calcium and magnesium ions all present. And under the right solubility conditions, these are going to combine to precipitate carbonates or calcium carbonate. We may get some substitution of magnesium for calcium that may form a dolomite, but we're more likely to see a calcium carbonate. These tend to form under the conditions that are ripe for that chemical reaction. And the chemical reaction is really going to be driven when we have warm temperatures and low pressures. When we get deep into the ocean, where temperatures cool off and pressures get higher just from the weight of all the overlying water, we actually get to a point where there is no more calcium carbonate. So really deep oceans aren't going to have any calcium carbonate developing. So we can also get another type of precipitation environment, which is when we have groundwater that is rich in these dissolved ions. So rather than occurring in the open ocean, this would be occurring in smaller springs and things. And these tend to be springs that are associated with volcanic activity. So most of the limestone precipitates in marine environments, but some is forming through ion-rich groundwater. And this forms a specific type of carbonate called a travertine deposit. So you can see some cool examples of this on the pictures. In this one, you're kind of getting a sense of like the layering as more and more of this groundwater is seeping to the surface. It's forming layers of travertine deposits that build up on each other. We also get these cool fungus-shaped travertine deposits. So the travertines tend to be layered, while the marine precipitation tends to create unlayered deposits. So that's one way to differentiate them. And then we can also get carbonates forming through biologic precipitation. So organic marine organisms are going to draw out the calcium and the carbonate, or the CO2, from the surrounding marine water and use that to build up shells. As they die and decompose, the shells often accumulate on the floor of the sea or the floor of the ocean, where they can then lithify or cement to form limestones. If they tend to be extremely fossiliferous, like this image I just circled, which, by the way, this living creature here is what forms these deposits. This is called a fossiliferous limestone because it's composed of shell fragments and fossils. We can also get micrite, which is formed. We have a fine carbonate mud and some shell fragments. So that's the second image here. And then as we keep going down in size, we do have tiny planktons that we can't even see with our naked eye. And as these die and settle to the floor, they form a type of carbonate called chalk. So just like the chalk we would use on a blackboard, this is composed of tiny plankton shells and is an example of biologically precipitated carbonates. All right. So last on our list of chemical rocks are the biological sedimentary rocks. And this is mostly going to take the form of coal. So as plant remains die and are deposited or kind of just sit where they died, and then eventually are buried to high pressures and temperatures, they transform from being kind of this loose carbon structure to a tighter packed carbon structure that forms coal. As that pressure and heat increases, we get more and more valuable forms of coal. So we start out with something called a peat, which is usually in a marshy environment. So we need these original environments to contain a lot of organic matter, like a marsh. And we also need them to not be eroded away. So it needs to be a fairly quiet environment. These are then subject to some pressure, which forms a lignite, which is a type of coal. However, it's not a very desirable type of coal. It's not very energy efficient. But as this is subjected to more pressure and heat, we start to get more and more valuable coals. So we get subbituminous, bituminous, and then anthrite at the highest pressures and heats. And so anthracite is going to be mined. Bituminous coal is sometimes also mined. But if the coal deposits are lignite or subbituminous, then they're not as valuable and often can be left where they are. Another type of biological rocks, which is one of my favorite rock types, is chert. So we talked about earlier chalk that was formed from tiny, tiny plankton made of carbonate. However, tiny plankton can also be made of silica, and as they die, form what's called a siliceous ooze. And then we call it an ooze because we can't really define individual parts to that ooze. When we look at the rocks that form from it, it looks almost like glass. There's no individual grains visible at all. And it tends to break in this conchoidal fracture. So you can see those kind of scalloped edges, a lot like how glass breaks. But if you could zoom into this, and note here the scale bar is 0.05 millimeters, you would see these individual diatoms that make up the siliceous ooze. And so these are those bodies that were made of silica that accumulate on the ocean floor and form chert. Okay, so now that we understand what the types of rocks are that can form these layers, let's figure out how can we interpret these rock layers. So when we look at these images, what can we draw out from them, right? And we've got some images from Earth here, but we've also got an image from Mars. So we see a lot of sedimentary rocks on Mars, and so there's a lot of impetus trying to understand what formed these rocks. So we can try and get at what Mars used to look like and see if there's a potential for life on other planetary bodies. So we'll ignore that little part in the corner. We start our journey here in interpreting sedimentary rocks back at Siccar Point. This is a location in the United Kingdom that kind of sparked a breakthrough in 1788. So geologists were looking at this rock and they noticed that there are kind of two patterns to it. There's a rock that has bedding that goes like this, that is horizontal, or vertical, sorry. And then that rock is suddenly truncated by another rock that has parallel bedding that is nearly horizontal. So we'll call it subhorizontal. And this led to a breakthrough of realizing that the ways that rocks are ordered tells us something about their geologic history. And it kind of relates back to Steno's principles here. And it's a nice way to tie that in and think about the vastness of time. So Steno's principles was created before the Siccar Point breakthrough. And it was a way in which we could relatively date rocks before we had the tools to give them absolute ages. It was created in 1669 by Nicholas Steno, who was a Danish scientist as well as a Catholic bishop. And there's three main principles that Steno originally came up with, and they're fairly intuitive, but they help us understand a lot about the rocks we look at. So the first one is the principle of original horizontality. And this basically says that all layers of rock are originally deposited in a flat plane, right? And this kind of makes sense. If we kind of look at the mud that's forming in a mud puddle, it tends to be forming fairly flat, right? With some exceptions being little ripples. So all rock layers made of rock deposits, really sedimentary rocks, were originally horizontal. And if they're not horizontal, we know that something has happened to them after deposition. The second principle is that of superposition, which basically means that younger things go on top of older things. Great analogy to this is your laundry pile, the first clothes that you threw down were the clothes that you wore longer ago, versus the clothes on top are the more recent clothes that you just wore. All of it should be washed though. So just like this, the rock layers form on top of each other. The rock layers on the bottom must be the oldest, and the rock layers on top must be the youngest. And then we have the third principle, which is cross-cutting relationships. I think of this as analogous to pickup sticks. So the first ones you throw down are then crossed over by the later ones that you've thrown down, right? So something that crosses something else must be younger than the original thing. So for example, in this rock layer in the bottom right, we have this gray rock that I've just outlined. And there is a white layer that cuts through it. That white layer must be younger than the gray rock that surrounds it. If it was older, the gray rock wouldn't be there for it to cut through. So that doesn't really make sense. So whatever it's cutting through has to be older. And the rock layers that cut through a layer are younger. So this black dike that cuts through both the white layer and the gray rock is younger than both of them. So this is going to be important, mostly when we have things like volcanic dikes and sills that are cutting across sedimentary rocks, or when we have things like faults that cut through. All right, so here's an example of how we can apply Steno's principles. Say we have a rock outcrop. Maybe this is a quarry and we're looking sideways at it. And we've identified 4 different rock types. There is a shale, a limestone, and a sandstone with an igneous rock that cuts through it. And based on those principles of superposition and cross-cutting and original horizontality, we can figure out which one of these was deposited first, right? So we know that C must be older than B because B lies on top of C. B is older than A, again, because A lies on top of B, so we're relying on superposition. And then D cuts through both A, B, and C. So that means D is younger than all of those. And then this fault, E, cuts through all of them, so it is the youngest. And this can tell us something about the environment, so we could interpret how the shale formed. It's the oldest rock, and it formed in some quiet environment. Then we get into a limestone, which would have been marine, and then a sandstone, which perhaps formed in a beach environment. So this allows us to look at how the water levels at the site have changed over time. We've gone from something that maybe was close to the ocean, maybe an estuary or a delta, to slightly deeper and warmer ocean conditions that are suitable for limestone and calcium carbonate precipitation. And then ocean levels must have fallen because now we're at a beach environment. Right? So that's one example of how to use Steno's principles. The last thing I want to talk about are the contacts between rocks, because this helps tell how much time has passed between each rock type. So there's 4 different contacts that we'll go through. And these are all non-conformable. So a conformable contact is when rocks are just deposited on top of each other in a steady sequence with no gaps in time. A non-conformity is going to occur when we have a non-sedimentary rock that is overlain by sedimentary rocks. So a really nice example of this nearby is the Great Unconformity, which is just outside Manitou Springs, and you'll see it as you are driving on I-24. And here we have the Pikes Peak granite, which is an igneous rock, and it is overlain by the Sawatch sandstone, which is a sedimentary rock. And so we have a boundary between a non-sedimentary and sedimentary, which leads to a non-conformity. This particular non-conformity is pretty unique. We've dated all these rocks, and there is about, in this gap of time between the 2 layers, is about 550 million years. So we're missing 550 million years of rock between the Pikes Peak granite and the Sawatch sandstone. Another type of contact are angular unconformities. And so now we're in contacts that are between sedimentary rocks. However, in this case, one sedimentary rock, the lower one, has undergone some tilting. And so it's no longer in its original horizontal position. So this is kind of what that first picture at Sicker Point was showing us, was an angular unconformity. And this is another great example of it in this top right image. We have some folded rock on the bottom. And so it's cutting at a non-horizontal angle. And then that is cut by this other rock, which is mostly horizontal. This example is from the Vriskin unconformity. So this was formed when Pangaea was created about 250 million years ago. Angular unconformities, like nonconformities, represent a lot of geologic time that's missing. Just like in nonconformities, the underlying rock, whether that's the granite or it's these tilted rocks, they have to be buried to great depths and then eroded back up to the surface before the top layer is deposited on top of it. In contrast, a disconformity, which is just an uneven layer between 2 sedimentary rocks, doesn't necessarily indicate that time is missing. So we often see these where stream channels have eroded into the deposit below them. And that stream channel erosion could occur over timescales of 1 to thousands of years. So it doesn't need to represent a lot of time that's missing. It could just represent a slight switch in the erosional process or depositional process going on. And then finally, one of the hardest unconformities to understand are paraconformities, because these are really not visible. These are two parallel rock units that have an erosional layer between them. So there is some time that is missing between them. In order to identify a paraconformity, we kind of need to know the ages of the rocks, or we may need to know some fossil assemblages that tell us that time has passed. Usually less amount of time has passed because there really couldn't have been any subsequent erosional event or any burial of the rock and lithification or tilting. All right, so we'll end on practicing geologic histories. So I'm not going to go through the answers to this, but I'd like you to pause here and spend a few minutes trying to back out which is the oldest rock, which is the youngest rock, and practice using terms like Steno's principles, original horizontality, angular unconformities, paraconformities. And then when you wrap that up, here's your homework. So we had this original question of how the world around you would look as a rock. And what I'd like you to do is to reassess your hypothesis from the beginning of the lecture and start to add more details to it. So for example, what type of sedimentary rock would it be? Is it clastic or chemical? What would you name it? What kind of grain size would you expect to see? The range of the sizes, the sorting, the angularity, and the textures within it. And as you do this, we'd like to practice tying observations to interpretation. So these predicted grain sizes here are interpretations. And I'd like you to tie that to what you know of that location, right? So for instance, I predict the rock will be a sandstone because my location is a beach. And this beach is made up of sands with no gravels or clays or silts. It's all one grain size, right? So practice doing that. And I expect that this would just be about a paragraph in length. All right, and this is the end of the Sedimentary Rocks lecture.